So this is a load deformation behavior of two columns which are having nearly same area, same amount of your longitudinal bars, and also one is having ties like this, individual ties, but another column is having spiral reinforcement. So continuously it is reinforced with spiral, right? So I take this column, right, and then I apply this load, right, and I start measuring, let's say from here to here, I measure this delta, and then if I start putting this load deformation curve, then this is the way two columns are going to be. So again, both the columns are having same area, okay, same steel, same longitudinal steel as well as your transverse. So if you look at the volumetric ratio of longitudinal bar as well as your transverse bar, both the columns are having same amount of steel, same area. So when I keep loading both the columns, you find that the tied columns are going to fail relatively in a brittle manner, and that will happen after this concrete cover. When you squeeze the column under compression, what will happen is this first the concrete cover which is outside this reinforcing cage, that will fall off. The moment the concrete cover falls off, the longitudinal bar will be unrestrained, okay, and it will be restrained only at the locations where you have ties. Then when you squeeze the column in compression, the longitudinal bar will start undergoing buckling. So that will lead to you have a brittle mode of failure. However, in case of a spirally reinforced column, what will happen is even after this concrete cover has spalled, now the reinforcement is continuous, and the confinement produced by the spiral reinforcement is going to be pretty good. So even so, what will happen is the load will start initially. If you look at it, both the red color curve and blue color curve are nearly same up to first peak. But the moment the concrete cover falls off, your longitudinal bar in a tied column, that will drop and it will fall. Okay. However, if you look at this red color curve, what we have is that is going to keep on resisting this load. So even this is your first peak. So you will have load drop because the concrete cover has now dropped off. Now when the column is getting squeezed, what will happen is you have the elastic modulus of this steel ties are going to be 200 into 10 to the power of 3 megapascal. So these are very stiff elements. So when the concrete is going to be squeezed, the concrete core is going to be getting squeezed. Now it is going to expand laterally. We have seen that damage mechanism of concrete under compression. So when the concrete is actually expanding in the lateral direction, now the spiral reinforcement will not let the concrete to expand. It is going to provide some lateral confinement. The more the concrete wants to expand, more will be the tightening effect of this spiral reinforcement. So it is going to put the concrete under lateral compression. So then the load capacity will start increasing, and finally it will reach its peak, and then the spiral reinforcement can also reach its yielding value. And you know that once the steel reaches yielding value, the stiffness of the steel reinforcement is going to drop down very drastically. So then it will start leading to load drop. Okay. So, but what we can see here is this is your, let's say, the delta U for a tie column. Okay. And you see here, this is the second peak if I'm taking. This is your delta U for spiral column. So you can see that because of the confinement of your spiral reinforcement, I am able to increase the deformation of failure or at failure. So you get significant increase in deformation at failure. So that is what we call that as a ductility. If a member is able to sustain the load for a very long deformation, then we call this member as ductile. So for a column that is reinforced with spiral reinforcement, because of the confinement effect, the behavior is more ductile compared to that of a tied column. So you can see here the tied and spiral columns with same cross-section areas of concrete and steel behave similarly up to ultimate load. However, ultimate load, the tied columns fail suddenly due to excessive cracking in the concrete, followed by buckling of the longitudinal bars, as we have seen in the previous slide. And then for spirally reinforced columns, once the ultimate load is reached, the cover will start falling off. However, now the concrete is going to dilate a lot. However, the dilation will be contained by the stiff spiral reinforcement. So that is going to confine the concrete core, and that will enable the column to sustain large deformation before the final collapse occurs. So that is the reason for a spirally reinforced column, the code is allowing you the PU not the pure axial compression capacity to be enhanced by 5%. So this is not from, because the column is very ductile, the code is recognizing that your column failure is not going to be brittle. So the code is saying that incentivizing for using spirally reinforcement by allowing some increase in your pure axial compression capacity. Now, so this is one video that I wanted to play. Was taken from YouTube. We not sure of the source. So if you look at it, this column was a square column. However, it was reinforced with a spiral reinforcement. So you can see here that as the load is getting increased, the concrete cover will initially spar like what we are seeing here. So this is the column that is being loaded. You will find that this is the load application that you have, and as the load is getting increased, you will find that the concrete initially cracking will happen, and then the concrete cover will start falling off, and then slowly you can see the cracking is happening here, and then you can see that the cover is actually falling off. So all this cover is falling off, and now the moment the concrete is fallen off, now you will find that now the concrete inside the core of the cage, it wants to expand laterally. However, that expansion will be contained by the stiff reinforcement that we have created, which is a transverse reinforcement. And you can see that even after the concrete covers falling, you can see that the load resistance is keep on going because it is the column is not completely failed. You see the reinforcement here. Right? So they are very closely spaced spiral reinforcement. So you get a pretty good, the load is sustained for a very long deformation. So even after reaching this kind of a failure mode, you are not seeing a complete failure. So you can see that the concrete cover has spalled over the entire region. So, so you can see that the concrete now core is trying to dilate, and that is being contained by this spiral reinforcement. And you can see the entire length of the column. Now you can see the concrete cover is pulled off, and you can see now the core is also trying to come out. So it is going to put lot of strain on the spiral reinforcement. You can also see that finally the spiral will also break. It will fracture, and the fracture strain of your reinforcement, we have know that for if depending upon the grade of steel, the fracture strain of the steel will be 12 to 13 or up to 15 percentage also. It is possible depending upon the grade of steel. So you can see that by having closely spaced spiral, we can really confine the concrete very well, and you will find that it's also see now the column is actually not vertical. You get this kind of a additional moment that is coming because now it has become the section is actually plastified, and the surrounding area of that. So now right. So in this one, you can also see the column failure will be the breakage. So you can see in this region the particular the spiral reinforcement has actually fractured. So you can see that you can see that the spiral reinforcement can clearly see it is actually fractured. So you can see by putting a spiral reinforcement or a helical reinforcement, you can really confine the concrete very well, and you can get very good ductility from the performance. Now let us see the code provisions, how they were derived for the minimum spiral or transverse reinforcement requirement. So now if I take a column, circular column, so we have seen that the diameter of the core is taken from usually center line to center line of this spiral reinforcement that we call them as DC. Now the spiral is at a pitch. So this is a pitch at a spacing of S. So if I take this 1 unit volume from, let's say, here to here, okay, and what would be the volume of the core within that particular spacing? It will be right, and what would be the volume of the spiral? So this is what we are saying is the volumetric ratio of spiral. Volumetric ratio of the spiral is given by volume of the spiral divided by the volume of the core. So now you can see here, this is your volume of your core concrete for a spacing for a unit volume between this one spacing that I'm considering. Pi by 4 times d square is your area. Area multiplied by S will give me this is your volume of your core. Volume of your core. Now, what would be the volume of spiral within the spacing of S? The circumference is again of the spiral that is moving is pi into DC. This is your perimeter. Okay, perimeter multiplied by the cross section area will give me volume of the spiral. So if you simplify this, then you get your volumetric ratio. Volumetric ratio of a spiral is volume of spiral divided by volume of core. So if you simplify this, you get this 4 ASP by DC times S. Okay. So if you know the spacing of the spiral, and if you know the area of the spiral, and if you know the diameter of your core, then you can calculate your volumetric ratio of your spiral reinforcement ratio. So this definition will be used in the next derivation for what is the minimum transverse or spiral reinforcement that is required. Okay, now you see, we talked about how that column is behaving. So if I take this free body diagram of only the core element, and what we have seen this is when your concrete core is getting squeezed in compression, it wants to expand in the lateral direction. However, the spiral, because it's a very stiff reinforcement, elastic modulus of the spiral is 200 into 10 to the power of 3, and your concrete elastic modulus is, depending upon the grade of concrete, 5000 square root of FCK. But usually steel is about 7 to 8 times stiffer than that of concrete. So the stiff steel, which is acting as a transverse reinforcement, it is going to restrain the dilation that is happening in this concrete core. So if I take the small uh, element, so if you look at it, this if you take the small element, and if you look at what are the kind of stress state that you will have, this will be the stress that will coming from applied compression. But this F2 is your lateral confining stress. Lateral confining stress. Okay, so so we know that whenever element is subjected to triaxial state of compression, it can take a very high strength to it will take very high strength and strain to fail that particular material. So now let us see how we have. See, basically, what people have said is if you test uh, a concrete cylinders under different levels of your lateral confining stress F2, let's say, then people have found that the difference between the confined concrete strength and unconfined concrete strength can be expressed as this simple expression, which is FCC is nothing but your confined concrete strength. Okay, concrete strength. This is your unconfined strength. So the difference between unconfined and confined strength, and this is 0.85, is actually coming from your size factor that we talked about, right? So every material, because we are doing testing in small cylinders and cubes, but in reality the elements are quite big, so you will have some defects that are possible in large specimens. So to account for this 0.85 factors there. So the difference between confined concrete strength and unconfined strength has been experimentally found that it is basically 4 times the lateral confining stress that I'm putting. Okay. So if you give me this F2, then I can calculate what is FCC in terms of F prime C. So what would be? So 0.85 FCC, then it will become 0.85 F prime C plus 4 times F2. If I'm giving you the value of F2, then you can plug it in this equation, you can find out what is FCC. This is what it happens. So if I take the small free body of this, let's say the spiral, then you'll find that this is your actually your F2, okay, which is a lateral confining stress. Because of that, now the spiral will be under tension. Okay, so we have to equate that, and you can find a relationship between the F2 and the stress in the spiral, what it is being created. Now we have found the expression for your rho s, which is a volumetric ratio of spiral as 4 ASP by DC times. Yes, that's what we did previously, right? Now let us see what are the relationship between F2 and the spiral ratio. So we have seen that from thin-walled pressure vessel, for a thin-walled pressure vessel which is subjected to an internal pressure, we can calculate your stress is hoop tensile stress as F2 times dc by 2t, or in other words, this is basically F2 times dc by 2t. That if this is a thin-walled pressure vessel of thickness T, then the stress in the lateral tensile stress is going to be, if I keep this FSP, then it is going to be F2 multiplied by dc by 2t. Now what is this? This is your lateral hoop tensile stress, and this is your internal pressure. Here it is actually lateral confining stress, and dc is your diameter of the tube, and t is your thickness of your tube. Now when you have a spiral at a particular spacing, or area of a spiral at a particular spacing, because in a spiral reinforcement the area of the spiral is moving along. Okay, if I convert that spiral as an equivalent tube, now the thickness will become ASP, area of the spiral, divided by the spacing. So if I convert the spiral cage into an equivalent tube, then the thickness of the equivalent tube is going to be area of the spiral divided by the spacing. So now if I go back and put it in terms of that, so you will find that what we are saying here is, as we have seen. So if I thickness, if I write that as ASP by S, then you will find that FSP multiplied by 2 ASP by S will be equal to F2 times DC times S, right? So this is basically all we are doing is basically T is equal to area of spiral by S. I am converting the spiral cage into equivalent thin tube. This is from a thin tube theory. So we know for a tube that is subjected to internal pressure, then we can calculate the hoop tension as F hoop tensile stresses, basically pressure multiplied by diameter divided by 2 times the thickness. So from this we have equated what will be the spiral stress into a lateral confining stress. So now let's see, if we simplify that, I can express my lateral confining stress as 2 into ASP divided by DCS times your stress in your spiral. And from our previous derivation, now what is that I want to do is I want to express instead of dealing in terms of area of a spiral, I want to cross-section area of spiral, I want to express in terms of volumetric ratio of spiral. So we have defined this volumetric ratio of spiral as 4 ASP by DC times S. So if I can somehow multiply this, right, in terms of, I want to express in terms of volumetric ratio. So this is the entire thing. You can see this entire thing can be written as basically rho s by 2. So if you substitute that, you will find, and what is the maximum the stress that particular spiral can take. Basically that is going to be when FSP becomes Fy, the yield stress, when this becomes equal to Fy, then that would be the maximum stress that particular spiral can offer. So if I replace FSP as Fy, which is the transverse reinforcement yield strength, if I'm using 415 grid, it will become 415, or if I'm using Fe500, it will become Fe500. So I can express F2 as 2 ASP times Fyt divided by DC times S, or in other words, the lateral confining stress can be expressed as volumetric ratio rho s multiplied by the yield strength divided by 2. So you can see here, how can I increase the maximum lateral confining stress? I need to put more rho s, or in other words, more area of steel or reduce the spacing. And also I can get higher value for Ft if I increase this yield strength of your transverse reinforcement or a spiral reinforcement. So if I put higher and higher grades of steel, then I can get more and more value of F2. or if I increase the volumetric ratio, I can get more value of your F2. So why is it we are interested in increasing that F2? We want F prime CC, which is your confined strength, is basically F prime C plus 4 times your F2. So I want to increase this F prime C. I want to increase the value of confined concrete strength. And let's say if I'm taking F prime C of 40, I want to make this F prime C into, let's say, 100. So I can calculate what F2 is required to increase the 40 to 100. So you can see I need to, for F2 should be now equal to 60. So F2 value should be at least equal to 15 megapascal. So to generate 15 megapascal, I can go back and calculate what is the volumetric ratio of your spiral reinforcement that is required. Okay, so in this way we can derive the expression. Now let us see using this how the code has calculated the minimum volumetric ratio. Again, why we take up this exercise was to find out what is the ROS that is minimum should be given and what is the rationale for coming up with this minimum volumetric ratio. So now let us see. For a tide or for a spiral column, we have seen that there was a first peak, then the concrete cover started spalling, then the load drop was there. But then, as the concrete core was dilating, again it was restrained by this spiral reinforcement. Then the load again picked up. So what that code is saying is, whatever that additional strength that is provided by spiral should be equal to the strength lost in falling of the concrete cover. Okay, so initially the entire cross section was taking the load resistance, but once the concrete cover falls off, only core area is resisting, so there will be a drop in load resistance. But again, there is a pickup in load resistance, so that pickup should be at least equal to what was the load was lost because of the concrete cover falling. So the load before and after spalling should be equal. That is the principle with which our the minimum volumetric spiral reinforcement ratio has been derived. So before spalling, we know that P1, if I call that, it is equal to 0.85 F prime C Ag minus AST plus. Okay, if I take the longitudinal bar as AST, you can take that as AS also. So it is 0.5 times AST. So we know this is the simple concrete contribution. This is steel contribution. And now after cover spalling, and now we cannot use the AG. Here I have to use only core area because the cover has spalled. So AG will not be there. AC I have to take. But here I am not going to deal with unconfined strength. Now I have to deal with confined strength FCC. So this is your again confined core strength and this is your steel strength. So what the code is saying is P1 should be at least equal to P2. So now let us relate this. And if you relate that, anyway, in columns usually we provide about 2%, 3% steel like that. So this contribution is not going to change. The code is saying that anyway both are going to be equal, so it is going to get uh, nullified. So you can quickly derive the relationship between FCC and F prime C. Or in other words, if I'm taking AST is going to be very small, then only the concrete contribution is a major contribution. So what we are saying is 0.85 F prime C times AG should be equal to 0.85 times FCC times your AC, because the AST is going to be very small compared to that of gross area or core area. So this is the then 0.85 will get cancelled. So I can relate FCC as F prime C AG by AC. So that is what we have got here, with an assumption that the area of the steel is going to be very small. And usually that's the case. It is 2%, 3%, or maximum we put about 4%. So we can relate that as now, if we go back again, from the experimental evidence, we have found that the difference between the confined strength and unconfined strength is basically 4 times your lateral confining stress. So I can again go back and put now what is 4F2, and 4F2 can be expressed in terms of volumetric ratio and transverse or spiral reinforcement yield strength in this form. Then if I further simplify that, we will find that basically again, why now we are talking in terms of F prime C, FCC are all cylinder strength. Now in IS code we want to convert everything into cube strength. So again, how do you convert the cube strength to cylinder strength? Cylinder strength is 80% of a cube strength, so that is the reason we are putting 0.8 multiplied, and then F prime C I am converting into characteristic strength or cube strength. So then it becomes zero point 0.8 times 0.85 by this. So once you simplify that, if you find expressions for your rho s, you can say that rho s will be, when you simplify it, you will get this kind of expression that has been rounded off to a slightly higher value. But the code, because when you put minimum reinforcement, code wants to be slightly conservative. So the code says, okay, if you look at clause 39.41, this 0.34 has been slightly increased to 0.36. So the rho is minimum what we need to put in your spiral reinforced column is basically 0.36 multiplied by Ag by Ac minus 1 times Fck by Fi. So again, what is the principle? What are the load lost due to spalling should be equal to the load gained because of the confinement. So using that logic, we have derived this expression for your minimum volumetric ratio. Now, how does this, again we said, how do we get that? So this was a very classical work. It was done by Richard et al. In as almost 100 years ago. So what he did is he took cylinders and put them under different lateral confining stress, and he tested them under uniaxial compression. But this is under hydrostatic stress because there's this F, whatever that we call, let's say this is, let me call this as, here it is written as FL, and this lateral confining stress is kept constant. But in your actual behavior, the FL will evolve slowly. Okay, so as the concrete is dilating, the FL will keep evolving over a period of time. But in this test, this FL was kept constant, and you see that when there is no confining stress for a 25 megapascal concrete, it failed at about 25 megapascal. But if I keep increasing this FL, say for example in the last case, if I am able to put the cylinder under lateral confining stress of 28 megapascal, the same 25 megapascal concrete grade, now it is failing at as high as 130 megapascal. So you can see, by putting the concrete under lateral confinement stress, I can get very good increase in strength. And also, if you look at the strain at failure, we know that a regular concrete is going to fail at a strain of, let's say, 0.0035 or 0.004. But you see this failure, it is going almost up to 0.05 so strain. So that means about 5% of strain at failure we are getting. It's a very large value. So this is the beauty with confinement. If I'm able to put the material under triaxial compression stress state, then I get very good strength improvement, as well as the strain at failure is going to increase. So this is what now people use for strengthening. So now the columns are very important members in buildings. So for example, if you want to put two or three more additional floors for an already constructed building, now axial load that is getting transferred to a ground floor column will increase. So now how do you increase the strength? By actually wrapping these existing columns, by wrapping them with fiber reinforced polymer material. These usually carbon FRP laminates or fabrics are used for confinement, and they have very high stiffness. So they actually act like a tube. So again, when the column is subjected to compression, then this provides confinement, and we can calculate what is the FL that is going to generate. Based on that, I can find out how much is the strength increase that it can have. So this is the evidence with which we derived that minimum reinforcement requirement for spiral columns. Okay, so this is just quickly to show, these are some of the columns that we have tested in our labs. So this was a column that was tested under eccentric compression, like what you have seen here. So you have a load that is applied here, right? And this is the center line of the column. So it is subjected to some eccentricity. So this column is actually subjected to both axial compression and bending, and you will find that this column is going to bend. So you can see this kind of a nice crack that will form, and you have multiple cracks that are forming. So this kind of eccentric compression, finally the column failed. Now we'll also see one more video of a spiral RC column that was tested under axial compression, and this was taken from YouTube. So you can see this is a bridge column which is spirally reinforced, and you can see there's a huge spalling of your concrete cover. Even after spalling, you can see that the column is not completely failing. However, it is able to contain the core and still able to resist the load for a very large uh, deformation. Right, so let us summarize what we have discussed in this part of the video. So we discussed what are slenderness limits and minimum eccentricities the code suggests, and we know why the code is suggesting minimum eccentricities to be considered. And we also talked about what are the minimum and maximum longitudinal reinforcement ratio, and what are the minimum transverse reinforcement, what should be the spacing between the longitudinal bars, minimum and maximum, all these things that we have discussed. And we also discussed how the code equation was derived to calculate the axial capacity of concentratedly loaded column. And we also discussed the difference between tied and spirally reinforced concrete column. And we also discussed what are the effect of confinement, right? Again, the confinement is a topic in itself, so you can look at specialized literature for further information. Yeah. So I would like to acknowledge the help of my MTech student, Mr. Ranjit Kumar, for helping with the slide preparation. So thank you.